way to do that is there's a facility available in the add-in. If you click Make K-fold columns, and then the typical way that it is to specify the Y response as in both this Y field and the stratification variable. And then if you just click Go, this will actually run a design of experiments routine called Fast Flexible Filling Design. And so this not only creates balanced partitions, but the actual folds that are created, which are added as variables to the table, turn out to be orthogonal. This is a nice property in terms of doing repeated K-fold in that it provides maximal information gain as we fit across these different folds. You can see the orthogonality by clicking on different levels of one fold. You can see how they're perfectly balanced in the other variables. So to use these folds in a repeated frame, we're going to fit each model 15 times and compare summary statistics across all of the folds. So let's now finally get into the modeling. If you click Add-ins, Torch Deep Learning, you get this initial setup window, which is similar to all jump predictive modeling platforms. We want to specify our weight gain as our Y response. And now let's set up our predictor variables. We'll do the baseline weight, critical Q smoking, which is our main effective interest. And then we're going to include all these other covariates, total of 14 variables in all. These are the same ones that Aaron and Robbins use. And then let's put our fold variables here as validation. Validation in this platform works differently from other jump predictive modeling platforms. It's similar to if you've ever used the XGBoost add-in, it works that same way where nominal fold variables like this will automatically do K-fold. If you want to do single holdouts, a trick is to create 0, 1 variables and convert their modeling type to continuous. We won't do that today. It's not recommended for a case like this. We want to do repeated K-fold in order to do more rigorous inference. Click OK, and we're now to the main launch dialog, or the model training framework for Torch Deep Learning. You can see a multi-layer perceptron is set up as the default model. Let's just go ahead and run the defaults and see what we've got. So you'll see a little progress window, and this is now, as I mentioned, training this model 15 different times, holding out each one of those folds in turn across the 3 different variables. So we're doing kind of a 5x3 framework here and collecting all of the results. And the key thing we want to look for when it's finished is how does the validation performance compare as we proceed across the number of epochs. So the number of epochs is the number of passes through the data that we perform while training. This graph has epochs on the x-axis and then the loss function that we want to minimize on the y. And typically what you want to see is, as here, this validation loss descends and then flattens out. So right out of the box, it looks like we've got a fairly reasonable fit here that we could potentially use directly for causal inference. For sake of illustration today, though, let's keep moving and play around a little bit with some of the parameters. As a first experiment, let's increase or multiply our learning rate by a factor of 10. So I'm switching it from 001 to 01. This effectively creates larger step sizes when doing the machine learning style optimization, which in this case is kind of a stochastic method known as ADAM. So it should theoretically train kind of 10 times faster, as it were, which is why it's called a learning rate. And now upon finishing, we see, in fact, that the model did achieve a minimum much faster. And then this blue curve is now going back up again. This is a case of mild overfitting. And so we would not want to use this model just because it's starting to overfit if we go out to 20 epochs. What we can do, though, is, given the nature of the curve, let's just stop our training after 5 epochs and see what that gives us. So this will be a third model that we can try. Training in this case is a little bit faster, as you can see, just because we're only going through the data 5 times instead of 20. And then to do a final comparison here on our 3 models, let's look at the standard root mean squared error performance metric. Depending on your objectives, you may want to use a different one. and several are available in the add-in. So the key column to look at here is val RMSE. We see our initial model had a value of 7.36. When you run this yourself, it may be a little bit different due to random seeds. As we saw in the graph, the second model got worse, all the way up to 744. And now with our third model, we're back down to 369, slightly worse than the original. So I view models 1 and 3 as effectively equivalent, just trained in slightly different ways. Now, here's where things get interesting. Under the advanced options panel, we have a whole suite of different modeling parameters that you can try. This illustrates the flexibility and power of a modern machine learning framework. We have things that we won't be able to get into today, but a lot of different options in terms of the layer sizes, the number of layers, activation functions, of which there's a whole suite of them available. ReLU being the most common, it's got a hockey stick. We have dropout, normalization. This is a factorization machine option, as well as other training methods designed to training. So the two columns of options here are roughly setup and then the training framework. Again, due to sake of time, we won't to look into these at depth now. But what you can do is mouse over each option to get a little tip on what it means and how to use it. For today, let's just try another little experiment here. One quick thing we can do, let's just cut the number of hidden nodes in half from 16 to 8 and see what happens. We'll use the quicker training framework. Again, you can see that training time here is virtually the model's a little bit smaller. And here we see that there was no actual improvement, just a slight change. So at this point, we haven't been able to improve even on the initial model. But what we can do is take a look here. We see it looks like this one's still going down. So let's try one final thing here. We'll bump that up now to 10 epochs and try it. Work very fun to play around in. It gives you a quick way to run experiments. So at least to me, helps you kind of understand and see the impact of each of these different parameters and in your particular data context. And what we can see happen here now in our final model, we were able to get actually almost, again, nearly identical results. So we're still pretty much there. All these models, at least all except I'd say these second models are roughly equivalent. So this was a case where the extra tuning didn't get a lot of payoff. Sometimes you can get dramatic changes depending on that initial setup. And a lot of data sets and things are different. This was a very well-behaved problem. So, and the default values happen to work quite well. So what we'll do is we've got some assurance now that tuning doesn't change things much. We can now proceed to our causal inference. And to do that, what we want to do now is if you scroll down, each model has more details behind it. So there's outline boxes for each of the numbered models. You can save these out if you want, or do other nice things. One thing that's very common to do, and let's just do this with our very first model, is the jump pro. This is a way to do kind of causal inference one at a time, where you actually, because you've got complete control over the values of each variable, and you can run what if scenarios, as many as you like. And again, our key focus here is what would have happened, what happens when we change this Q smoke variable from 0 to 1. And you can do that here by clicking. Sometimes the profiler for this model can take a little while depending on the complexity of the model, but you can see what happened there. Our prediction jumped up. And so when these other covariates are set at the levels shown here, we actually have an individual causal estimate, which you can do by remembering the settings and computing a difference. And there's one example of an individual causal effect at specific covariates. Now, for our purposes, we can get them all at once if we just save all the predicted values out to the table. So I'm clicking just a red triangle, save predicteds. This creates a new predicted value column in the table, which includes not only predictions for the original data, but most importantly, for all of our counterfactual values. And all that remains at this point then is to compute differences between those two, which we can get to with a simple split operation. So let's split that variable, splitting it by QSmoke, and we'll use this secn as our ID variable just for saving the table. And then all we have to do now, I'm doing right click, new formula column, combine, difference, and let's do reverse order. So we get 1 minus 0. So this is the causal effect of quitting smoking, computed individually for each person. We can see what happens overall with the distribution. Let's see what we've got. And it looks like we've got a nice kind of bell-shaped set of effects here with a mean value of 3.17. Remember that 90 that we had at the very beginning, 2.5. Looks like the actual, much more rigorous causal estimate based on this torched deep learning response model and the covariate adjustments is actually 3.2 overall. However, if we look at the individual estimates, they range quite a bit, from 6 all the way down to 0. And I find this is a very intuitive way to perform causal inference and very practical in terms of kind of personalized estimates of the causal effect, all made possible by our more advanced machine learning framework. Now, to wrap up, before we wrap up, let's show one more thing. There are many different ways to perform inference, and one popular way that you've likely heard of is called propensity scoring. What propensity scoring involves is fitting a preliminary model, kind of a secondary model, that computes probabilities of receiving the treatment. Turns out we can do that easily also in our framework. All we need to do is change our variable, what we're predicting. We're not going to do the weight gain anymore. Instead, we're going to use the Q smoking variable. There's a variable in the table here called QSmokeY, which has missing values for the counterfactuals. You wouldn't want to use the original one because it's perfectly balanced and you just get a completely nonsensical, meaningless model over perfectly balanced data. Here, though, we're back to our original treatment assignments only in the 1566 original data. We don't want to put QSmoke in our model naturally, but we will use all the other covariates now to develop a propensity scoring model. And now our response is binary instead of continuous. When we make that change, you can see the only thing that changed was this loss function is now binary. We use binary cross entropy, and let's see what happens when we train it. We're again using 3x5 repeated k-fold with the same folds as before. But now we have a totally different response, and you can see what happened here. Looks like the model is actually doing reasonably well again, kind of bottoming out just after 4 epochs and staying flat. So you could actually retune this a little bit more if you wanted to get a little bit better performance. This seems pretty reasonable for computing propensity scores. And then the detailed output is a little different. For a nominal variable, we get prob actual values, which are exactly what we want to use when we do propensity scoring, as well as the standard confusion matrices, ROC curves. We've got some new precision recall curves coming as well, and model details just like before. So that's the way you can use the same framework for propensity score modeling. Well, I hope you've enjoyed this initial introduction to the Torch Deep Learning add-in. There's a lot more we can cover, but I'm hoping you get the feel for it. There is a lot there which might be intimidating at first, but if you take the time to go through it carefully, I think you'll find it very powerful and enable you to do some really impressive things with your modeling, including now a modern causal inference. Thanks for listening.